Alrighty, apologies for the delay, technical difficulties. Okay, so, yeah. All right. Okay, so yeah, so my name is Jonathan. I'll be talking today about DisCoCirc, which is a model for natural language. So the structure of this talk is a little bit lopsided because it's kind of, we merged two submissions together. So in the first half, I'll be talking more about a kind of theory paper that's joint work with Vincent and Bob, as you can see there. But then in the second half, we're going to delve more into like applications and stuff, which is work that a lot of people at Continuum and Oxford contributed to. Okay, so first off, why do we care about this thing? Yeah, so DisCoCirc is a model for natural language. And I'm going to give three concrete reasons for why we find it interesting. So firstly, we think that it is interesting because it's a structured and inherently interpretable machine learning model. And so for those of you familiar with deep learning, interpretability is a bit of a buzzword these days. And the idea is that you have all these fantastic cutting edge architectures, models like ChatGPT that can do incredible things, but they are opaque black boxes. You don't know how they work inside, how they get to their answers. Sometimes they make mistakes and you don't know why, you don't know when they'll make mistakes. And so this opaqueness has a whole host of problems. So within deep learning, there is a movement to try and, instead of taking these models, to instead try and build inherently interpretable models that we can understand to some extent. So DisCoCirc, we think, falls under this umbrella. Secondly, we think, or we hope, that DisCoCirc can serve to bridge the rather large gulf that currently exists between linguistic theory and natural language processing practice these days, especially with respect to incorporating deep learning methods in a very native way. And finally, we think that DisCoCirc is interesting because it's a model that we can and we hope to run very soon on a quantum computer. And the version of it that we will be running on a quantum computer will be a version of the model that is not classically simulable. And so that's very exciting. Okay, so to give a bit of background, so DisCoCirc falls under this family of so-called distributional compositional models of meaning. These models are quite tightly related to QNLP models. It all kind of started with the DisCoCat model being introduced in 2010. And the key insight that actually led to the creation of that was that, so quantum processes and certain typological grammars have a kind of shared underlying categorical structure. And this insight allowed us to create, well, not us, but the creators, to make this model that combines vectorial and structured approaches to NLP. And in particular, grammar is used as a proxy for the flow of information. And so DisCoCat was applied successfully to various NLP tasks, but it had a big restriction, which is that it was only restricted to sentences. Like using DisCoCat, you can model constituents up to and including the level of sentences, but you can't go beyond that. So that kind of restricts the kinds of tasks and the kinds of things that you can do with it. And so in 2021, this new model DisCoCirc was introduced. And the reference I put there is not actually the original paper, but it's the one that we would point you to now today. So this model was introduced, and it shares a lot of the kind of essence of DisCoCat in that it's like kind of string diagram flavored. It's both compositional and distributional. But DisCoCirc is able to model general text instead of just sentences. And the key philosophy here is that text is viewed as a compositional meaning update process. And furthermore, we think that while we've been talking about it in this kind of NLP NLP context, DisCoCirc can be a very general model, and it can be applied to many modalities and with many semantics. And I'll go into the different semantics a bit later. So just to give an idea of how this works, consider the sentence "Alice likes Bob." So the DisCoCat diagram for that sentence, which we all know and love, is the thing on the left. We read the diagrams from top to bottom here. So the key point here is that in DisCoCat, every sentence ends up having one sentence type output, right? So it just ends up being a vector in some sort of sentence space. Meanwhile, in DisCoCirc, the diagram looks like the thing on the right. And the key idea here is that in the sentence, there are two entities, or in semantics, you might call them discourse referents, Alice and Bob, and they both each have a wire, which carries information about them. And meanwhile, the content of the sentence is captured here by the verb likes, and that is represented as a gate that acts on these wires and serves to update the information in some way. And so let's take another sentence now, as Alice dislikes Claire, which has the corresponding DisCoCirc diagram as shown. So what you can do now with DisCoCirc is view these two sentences together as one coherent text and represent them using one text circuit representation. And so here we've just basically noticed that Alice appears in both sentences rather, and then just plug the wire together sequentially. Okay, so that's one kind of composition that we have in DisCoCirc. There's another one here which I'll illustrate using this sentence: Alice sees Bob drunkenly dance. So drunkenly dance you can think of as a verb, so just a box acting on a wire. But then you can kind of peer inside it and realize that you can factorize it into a simple verb dance and then an adverb drunkenly. And in linguistics, it's well motivated that adverbs, you can think of them kind of as like a higher order function that takes in a verb and returns a modified verb. And so in DisCoCirc, we have this kind of syntax with this like what we call a frame, which is like a box with a hole, which is how we depict these higher order functions. And so the DisCoCirc diagram for this entire sentence would look something like this. And you notice that sees here also becomes a frame because Bob sees, Alice sees Bob drunkenly dance. Okay, so one cool thing about this kind of 2D representation of meaning is that we hypothesize that a lot of the complexity of grammar and various other kind of linguistic conventions arises because you're trying to force meaning into a one-dimensional string. So as humans, for example, when we talk to each other, we have to use a sequence of noises, right? And when we write things, we write a string of symbols. Because DisCoCirc kind of goes into this higher dimensional space in its representation, it does away with a lot of these conventions. And we've coined kind of a word or two, or rather two, for this thing, this phenomenon, which we call intra-language independence and inter-language independence. And so intra-language independence is the idea that within the language, there are many different ways to say things that are essentially the same. As you can see by the two example sentences on the left in English. But then these differences disappear once you kind of move into the circuit representation. And meanwhile, inter-language independence refers to like differences between different natural languages, right? Which there are a lot of conventions that also kind of vanish when you move into the circuit world. So here on the right, you have an equivalent sentence in French, and they all kind of get mapped to essentially the same thing. Yes, on this latter point about inter-language independence, we did some work comparing like Urdu and English, a very simple fragment. Essentially, the gist is that we take this simple fragment, we equip it with some grammar, and then when you draw it as a circuit, it ends up being the same circuit with some labels different. Okay, so to go a bit more in depth into how these circuits work. So the circuits are essentially freely generated from a bunch of components. Nouns or discourse referents are these states that we've seen. Verbs are these gates that act on these noun wires, and they can have different arities depending on how many nouns are involved. Adjectives also are usually gates. And then we have adverbs, which we saw already is a frame, a higher order function. And again, the same kind of words might have a different shape depending on the different arity and the context in which it appears. Some more things, so adpositions, it's also a very important part of speech. So the example here is John runs to the shops. And the idea is with adpositions is that it kind of links something to something else. And here you kind of bring in this additional noun into this gate. We also had something we called verbs with sentential complement, which the C's from before was an example of that, where you just have, again, a frame that kind of takes in some arbitrary circuit, and then you can plug things in as you will. And yeah, just a few more things. So we also can deal with conjunctions. Again, this is all syntactic. But yeah, we can have a conjunction of two kind of sentences or clauses, here represented by C1, C2. You can have conjunctions of nouns. So Alice or Bob dances. And then, yeah, another structural thing that we have are these reflexive pronoun boxes. So sometimes you need to juggle the wires around a bit. So to represent Bob likes himself, we can draw something like this. And so a result from the paper, the big paper, which is what the first half is about, is that you can get a lot of mileage just from having these circuit components in terms of modeling natural language semantics and grammar. And in particular, we kind of demonstrated that there was a surjection from a certain fragment of English text to a certain fragment of text circuits. And the kind of cartoon at the top shows you how we translate that. Yeah, and in order to do this, we invented this kind of toy grammar called hybrid grammar. It's not meant to be a realistic model of grammar, but it's just something we invented so that we could just do this proof. And essentially, we just took a few ideas from various places. Like we have these generative context-free grammar rules, and then we have some like co-reference resolution things, which are the these arrows beneath the sentence, and then a few other things like phrase scope and stuff. So before, when I said the set of English texts, it was the set of English texts equipped with this grammar, this grammatical structure. Okay, and since this this map from text circuits to from English text to text circuits was a surjection, you get these kind of equations between language, like expressions in natural language, essentially, by taking the equivalence classes of the inverse images under this map, right? And we kind of already saw that, where you have different sentences in English which map to the same circuit, and so we consider them semantically equivalent. And then you can do cool things like you can extend this grammar by like enforcing additional equations between things that you think should be semantically equivalent, and these correspond to adding in more like graphical rewrite rules into your system, and from which you can build more proofs and stuff out of that. So now to switch gears into something a bit more applied. Richie kind of stole my thunder a bit in the last talk with this, but so yeah, this is joint work with Richie and a few other people at Continuum. Over the last kind of year or so, we built this software, which is essentially a parser for DisCoCirc, for text circuits. You put in English text as input, and you get text circuits out as output. And the thing on the right here, which you're not meant to be able to read, but that's something that is output by our software. I think it's a story about the hare and the tortoise having a race or something. And this is actually a DisCoCat diagram. So we'll shout out there. And yeah, primarily for this software, it's mainly built on top of a combinatorial categorical grammar parser. And additionally, we also use some co-reference tools and stuff to deal with like matching entities, that kind of thing. And yeah, and the software basically covers everything in the big paper. Yes. Yeah, so it's kind of both. So we call it a pipeline because there's different steps. The CCG parser is some black box transformer, I think. Then once we get the output from that, the rest of the process is deterministic. Yeah, but the CCG parser could like suggest different parsers for the same sentence, and if you took a different one, then you would get something else. So yeah. So if you put in kind of anything from the big theory paper into the software, it basically should spit out the right diagram. And so this software is not open source yet. We're planning on making it open source as soon as possible. But in the meantime, a few of us internally have been kind of playing around with it to do some things. And so we've been using the outputs of this parser to try and do these the set of very simple question answering NLP tasks called the Babby tasks. They're fairly simple, as you can see. Like there's an example here. Mary went to the bathroom. John moved to the hallway. Mary traveled to the office. And the question is, where is Mary? And the answer is that Mary's in the office. So what we can do with this is that we take the context sentences and then we convert them into a context circuit, right, representing the content of that context, which you see on the left. Just as a quick note, here is like the kind of word to should be like a frame. This kind of sandwich thing is just one way that we've chosen how to deal with frames in our experiments. And then, so once you have this context circuit, well, the question is, how do we extract the information from the context circuit in order to actually do the question answering? And this is not immediately obvious, and we tried a bunch of different approaches, and there were a few that worked. One that we kind of like, because it's kind of interpretable, is that we kind of test the different wires at the bottom for relations. And so in this case, you can see that, so this wire here, if you track it, corresponds to Mary. And if you want to know where is Mary, you basically feed the Mary wire into these boxes and then check it against every other wire to see if Mary is in the bathroom or in the hallway. And the kind of result of this measurement, which I've depicted as the dotted lines here, will just be like some probabilities, for example. And then to get the answer, you just take like the argmax of those probabilities. So that's one way that we've dealt with that. So yeah, I mentioned before that DisCoCirc, you can give it different semantics, so different ways of filling the boxes. One thing that we've done, as you've seen in Richie's talk, is just interpret the boxes as classical neural nets. And so yeah, you've already seen this graphic, but you can start from this diagram here, and then you get this Keras, this computational graph from Keras representing the neural network here. An important note is that in this version, the categorical monoidal product in the diagram is like a direct sum or a concatenation of vectors, rather than an actual tensor product of vectors. Yeah. And here are some results for it. So I don't want to like overstate what we've done, because the kind of tasks that we're doing are like, they are toy tasks. If you take any advanced architecture, it could probably do pretty well on it, get 100%. But nevertheless, for the baseline here, this is from an LSTM. And we actually, so these two approaches are both our models. And for the tasks that we've done so far, we significantly outperform the LSTM baseline, which is pretty cool. And so yeah, here we've got some examples of the kinds of tasks that we've been able to do. And so you can see there's like various different logical structures and patterns. You have like yes and no, you have negation, you have like indefinites, that kind of thing. And the samples get much longer than just 3 sentences. Like sometimes the context can get very deep and very long. So yeah, and so for an alternative semantics, we have the quantum circuit version, which yeah, so you can take the diagram as usual and then fill in the boxes with these parameterized quantum circuit ansatz, and you get this circuit with a bunch of trainable parameters. And importantly, in this interpretation, the categorical monoidal product is a tensor product, and so it's not classically simulable if it gets large. So in terms of future directions, there are lots of things that we want to try with this. It's a fairly new idea. We haven't really explored like a lot. There's many different things that we want to do with it. One thing that's interesting is to compare the quantum and the classical version to see how they stack up. Does the structure of the tensor product and having quantum entanglement buy you anything? We have some preliminary results maybe in that direction. The other thing that's a big question for us to answer is like, okay, we say that this model is interpretable, and intuitively it seems to be the case, but what exactly do we mean by that? How exactly do we characterize that? So that's a big question. And then I guess lastly, just from the more theoretical linguistics perspective, how can we expand this model to model more of English, to model more linguistic phenomena, and just more abstractly, how far can we go by doing formal linguistics or formal semantics just using string diagrams, essentially. And yeah, here are some references, and that is all. Thank you.
Great. Thanks very much, Jonathan. Yeah, any questions?
Well, I'll preface this by saying I don't know anything about quantum mechanics, but when you say non-classically simulable, does that just mean it would take forever, or it's like something in the problem that is literally preventing it from?
It's forever. It's just the complexity is too high.
Gotcha. Thank you.
Fascinating. I have a question about the direction you're going in. Beyond semantics, there's always the issue of interpretation. In political, geopolitical analysis of texts, it's not only what does the text say, but what does it imply about what the sayer believed. Do you have an interest in that kind of? It's sort of an inverse problem. You view the text as a signal from a belief system or an intention. Do you have any interest in going in that direction?
Yeah, it's an interesting question. I don't think it's something we've thought about, but I mean, if you have ideas for how we could use this thing, yeah, I'd be more than happy to chat.
Yeah, so Could you say a little bit more about how in DiscoPy you're representing the nestedness of the frames? Like the frames can be arbitrarily nested, right? How does that work?
Yeah, okay. So I avoided going into the nitty-gritty details of the pipeline software, but essentially we don't actually store them as DiscoPy diagrams. That's kind of the last step. The actual underlying data structure that we use to represent these things is essentially something similar to a simply typed lambda calculus term. And so that kind of has a very natural way for you to deal with these higher order functions and stuff. Probably, yeah. Yeah.
I have a question about it, like, because you want to interpret these in Hilbert spaces or categories which don't have comonoid structures. Like you don't have comonoid structures, but like linguistically, it seems pretty natural to me, like that when you have a noun, you should be able to split it. Is there like a linguistic argument why that doesn't make sense, or do you only not split it because you want to interpret it on a quantum computer?
So you're asking if there's a linguistic reason to not have splits?
To not have comonoid structure on your nouns.
Yeah. Short answer, I'm not aware of any. Yeah, I don't have a good, I have some half-baked answers I could give, but I don't think there are, yeah, I won't share them.
Let's take the online question and then we'll come back.
Yeah, so I have a question from Leader Strumpf saying, when will you open source it, i.e. what will trigger it? Unfortunately, this is in the hands of the corporate machine at the moment. And so we would love to have this out there as soon as possible, but yeah, certain things need to be done before we can do that. As a rough timeline, maybe on the order of 3 months, 6 months, I don't know, something like that. So not immediately, but yeah, hopefully soon, yeah.
Let's take one more and then we'd better move on to the next.
Oh, yeah. Sorry, this may be a basic question, but from what I gathered, you take some natural language and then you turn it into this diagram form, and then you can translate that into a neural network, but I didn't quite get what the neural network is intended to compute, or what do you actually do with that in the end?
That's a good question. No, so the context circuit by itself as a neural network is essentially meaningless. Like it only becomes meaningful when you have a task, you have something at the bottom to attach to it, and then you have a loss function which you can train to some purpose. At the moment we don't have, like the circuit by itself, we don't have a way to think about how to just train that by itself. Yeah.
Great. So sorry, there are some more questions online and some more questions in the room, but we'll have to move those. You can always discuss on Zulip, remember. There's a Zulip channel. Next, you can get the microphone. Sorry, I was just saying to people online that we'll have to take those questions onto Zulip to discuss them, because next up is Owen. Have you got a...
My computer won't connect to Wi-Fi, so I used the hotspot to put my talks on my website. So just gonna open them up here, if that's possible. Okay. James told me to stop the recording, and then